Hello. In this presentation, I will describe a variational inference method called semi-implicit variational inference. This method of approximate inference attempts to make variational inference more accurate by introducing more expressive variational distributions. Specifically, it introduces the semi-implicit distributions. Unlike standard explicit distributions that have a closed or analytic form, these distributions are a result of transforming random noise through a potentially nonlinear set of transformations. These transformations could be a physical simulation or a nonlinear model, such as a deep neural network. Unlike standard distributions such as Gaussian, Dirichlet, or exponential distributions, the resulting distribution has no explicit analytic form, but we are still able to sample from it, as we have represented the process that generates these distributions from random noise. So before we start, let's first review a little background on model and variational inference. In model inference, we are interested in learning the distribution of some unknown or hidden variables z given data or observations x. Rather than explicitly specifying this distribution, typically, it's easier to specify a prior distribution, pz, and a model likelihood, px given z, and then use Bayes' rule to derive the posterior distribution, pz given x. For example, in the naive Bayes classifier, it's easier to specify that, given the hidden class C, the observations follow some distribution, such as a normal distribution, with mean and variance. We can then put a prior, such as a Dirichlet distribution, on how likely each class of the model is expected to appear. On the other hand, specifying the probability of the class given the observations directly is less obvious without the above procedure. Because of our choice in specifying the prior pz and the model likelihood px given z, the resulting posterior distribution tends to be complicated and has no analytic solutions except for very simple models. Variational inference tries to solve this intractability by approximating pz given x with a variational distribution qz. This is accomplished by minimizing the relative entropy, or KL divergence of qz and pz given x. Here, we can see that the KL term can be broken into two parts. The first part is entirely dependent on the model and can't be optimized by changing q. However, the second part, e log q minus log p, depends on q and can be optimized. To minimize the KL, we need to minimize this term with respect to q, or equivalently, maximize negative e log q minus log p. This term is also called the evidence lower bound, or ELBO for short. Note here that q is a distribution on the hidden variables and doesn't explicitly need to depend on data. However, intuitively, a good distribution q should relate or be optimized in a way that fits well to the data. We can see if that q is from a very expressive family. Our original posterior p could be approximated arbitrarily well by q. However, it is hard to find an expressive family of distributions qz to approximate pz given x that is widely applicable to many models. One example is mean field variational inference, where each hidden variable is assumed to be independent of the others and given an explicit univariate distribution, such as a Gaussian. However, this independence assumption is very restrictive, as the hidden variables could potentially be correlated. So the idea of SIVI is to define qz by breaking it up into q psi z given psi and q phi psi. Here, psi and phi are the parameters of both distributions respectively. qz given psi is an explicit distribution, such as a Gaussian, but q phi psi can be an implicit distribution, where we need only to be able to sample from the psis. Because of this, q phi psi can be made to be very expressive. For example, it could be defined by a physical simulation process, or a very complex model such as a neural network, where we can generate samples by transforming random noise using this model or simulation. Here, the model or simulation is denoted as t. With this, we are able to approximate qz by Monte Carlo sampling the size to approximate the marginalization integral. Let's denote this variational family as h phi z. The name semi-implicit comes from the fact that we have two approximating distributions. One is explicit, while the other is implicit. Now, the variational parameters that we need to optimize is phi and psi, the parameters of the noise transformation, and the parameters for the explicit distribution. However, the optimization of this model is still difficult due to a KL term of the mixture distributions. To optimize with respect to these variables, we can derive a lower bound to the ELBO, which justifies minimizing with respect to the average of the KL terms, instead of the KL of the mixture distribution. This means we can compute the KL of each sample parameter psi and average them to approximate it, instead of having to compute the KL of the distribution of all samples. This lower bound can be derived as follows. First, by convexity of KL with respect to Q, the KL of the expectation is less than or equal to the expectation of the KL. We can then break the ELBO such that it is written as a KL of an expectation. And then, switching the KL and expectation operations around, we can get a lower bound to the ELBO. This lower bound is denoted as L underbar. As mentioned previously, this is easier to compute as it can be approximated by a sum of KL terms instead of a KL divergence of a complicated mixture of distributions. However, with this approximation, the optimal solution of q phi psi is merely a point mass at the optimal psi. To see this, note that L underbar is an average with respect to the distribution q phi psi. If we want this term to be as large as possible, we would only pick the distribution with a point mass at psi star, the psi star that maximizes the term inside the expectation. Thus, optimizing this lower bound to the ELBO could lead to solutions that degenerate to ordinary variational inference. To prevent this degeneracy, the lower bound is regularized by adding the term bk. Intuitively, as k approaches infinity, the term hk tilde becomes closer and closer to our true variational family h phi. With larger and larger k, we get a tighter lower bound to the ELBO, giving us finer and finer approximations of it. Moreover, this term is 0 if and only if k equals 0 or q phi psi degenerates to a point mass density. Thus, maximizing this term would drive q phi psi away from degeneracy. We can also derive an upper bound to the ELBO. Similarly, this upper bound converges to the exact ELBO as k goes to infinity. However, we will only be using the lower bound in our optimization algorithm, and the derivation for the upper bound is omitted from this presentation. So the optimization algorithm is as follows. Firstly, you get a new mini-batch of m data points. For this set of m data points, we sample j parameter value psi and j hidden variable z. Using these sample values and the m data points, we compute the lower bound to the ELBO that we described earlier as a function of the parameter values of the implicit distribution q phi psi and q psi z given psi, the explicit distribution. Using this, we can now compute gradients with respect to the parameters psi and phi and update them accordingly. We can repeat this procedure until all parameters have converged. In conclusion, the idea of SIVI is motivated by finding a method that harnesses the expressive capability of complex simulators, such as deep neural networks, and use them for approximate inference. With this perspective, the neural network can be thought of merely as an optimization device to find a suitable variational distribution that fits our true model fairly well. This is achieved by reparametrizing the variational distribution such that it consists of two parts. One is an explicitly defined distribution, and another that is implicitly defined through sampling from a complex model. That is the end of this presentation. Thanks for listening.